I will record this meeting and I will publish on the YouTube channel, and you can see, you can watch the next after that, after this meeting. And hi everybody again. I hope everybody is okay. Today we will talk about what we did in a week. If you have any suggestion after the presentation or problem, we can talk about them as well. And yes, we can start the first group. Gabriela and Batuhan, if you want to start to tell about
Hello.
Yes, hello.
Yeah, we can start with our presentation.
Thank you.
It's okay if we share the screen?
Yes, okay.
I think you can see the presentation, right?
Yes, we can.
Okay. So our choice of image representation was novel enhanced quantum representation of digital images, and it's released on 2013. At that approach, they encoded the pixel values and also the pixel locations using a summation and representing them as qubits. And this is the closed form of it. It's actually like a tensor product of image location and pixel values. And as you see in here, that qubit represents the pixel value depending on the image intensity levels. And this one represents the pixel location. So to represent a 2 to the n times 2 to the n times image, you need 2 times n plus q qubits totally. And 2n qubits is just for representing the pixel positions.
Okay.
So we can call it spatial positions. And also we need n qubits for pixel intensity. For example, if our image is grayscale image, so q is going to be 8 basically. So that's just logarithm of the value. And this is an example of 2 times 2 grayscale image. Since it's a grayscale image, q is 8. And since it's 2 times 2, n is 1. And this is the digital image representation for humans. And this is the bitwise representation. And since it's 8 bits, we can represent it using 8 bits. And this is the image encoding into a quantum state. As you see, the first element of that tensor product represents the pixel value, as you see in here. And second element of the tensor product represents its position. So it's like 0, 0, 0, 1, 1, 0, 1, 1, like first pixel, second pixel, third pixel, and fourth pixel. And we sum that multi-tensor products and divided by 2, so we can represent the image in the quantum state. So this is the simple sample image we use for making our tests. And this is the input image. And this is the output image after we encoded it using an EQR. And this is the quantum circuit to represent it. And as you see, 8 bits for pixel values and 2 qubits for pixel positions. And we implemented it using CNAT gates. And then we had a measurement to get the output image. And this is another test image. We just tried to see what is the circuit look like with bigger images or images with different gray values. As you see in here also, we have different gray values in here, full black, full white, and also some values between black and white. So some shades of the gray. And as you see, since this image is 8 by 8, and now you see the qubits for pixel positions is also increased. But as you see, qubits to represent intensity is still same, because this is again a grayscale image. So only thing we increased is pixel positions. And also we represented it using just CNOT gates. And while we are simulating our circuits, we have faced some problems. And the problems is about image size and pixel values. So due to those problems, we had very long circuit compilation times. So to overcome with this is a solution, we tried to resize images, so like downsampling them to a smaller version of them. And also we tried to inverting the pixel values to see if it can bring some solution, because as you know, if the pixel value is 0, you don't need to apply any quantum gates if it's just pure black, so 0 value. But if it's not black, then you need to apply some quantum gates to get the expected value. So from now on, I leave this stage for the Gabriela, so she can show us our experiments and make a presentation of it.
Yeah, right now I'll show our code implementation and also talk a little bit more about how we encounter those problems and dealt with it. Here is the code that is already available on the GitHub repository in our QR branch. So we did it full automated, and the way it's done, you just need to change the image path here and the size you want the image, because as Han said previously, we have a lot of problems with circuit size, because we automated all the circuit, and then we chose a image from the dataset to implement, which is this one in here. Just pick example from the dataset, and it is a 70 by 70 pixels image. So, and when we went to run it, it generated a really big circuit. So, and so big that in my computer, I left it running, and even after 48 hours, the simulation didn't stop, and I needed to kill it. So because of that, we needed to resize the image to a smaller size, because it was unfeasible to do the original size. And we resized it to 32 by 32, and we actually managed to simulate it in 4.5 hours. What was still too big. Then we analyzing the image and taking advantage of the dataset images being all simple shapes drawn in grayscale. We realized that we can use that information to compress the circuits, because here in the image, as you can see, it has a white background and a black image drawn into it. And as Juan previously said, white has the biggest grayscale value, 255. So it also needs the most amount of operators to be represented, while black, on the other hand, doesn't need any operators to be represented. So what we did is we inverted the image, so then we would become black background with white symbol drawn into it. And so in a way we could compress the circuit, because it's just a grayscale value, so we can invert it without losing any information. We can use that, and it actually had great results. The original image went to 4.5 hours to 30 minutes, or around 30 minutes to be implemented. And I also brought another example here to show how this compression works. So it's the same image that Hans showed. So the original image is this 8 by 8 image with a blackish square in the middle. So I already run all the circuits here just to be quicker. And when the circuit generated by it, as you can see, is really big. And every one of those background pixels here, as you can see, you need to control all the bits. So you need a lot of operators to represent it. And it's a really big circuit.
Yeah.
It goes from here. And the size of it, which is the secret size, is the amount of operators the secret has. It's 726. And it took 46 seconds to simulate this small image. And here is the original image, and here is the original image against the generated image. Because with the advantage of NRQR is that it always can return the original image without any loss, because is the actual grayscale values that are implemented there. So now when I pick this image and invert it and run it, it's really quick, so I can run it right now. It will generate even this small 8x8 image will already have a good compression. So as you can see here, all of those bits that were 255 pixels now became 0 pixels and doesn't need any operators to be represented. Like all of those huge circuits now became this way smaller circuit here. It's still big, but way smaller. All of those barriers represent a pixel. Every pixel is separated by a barrier. And the circuit shrinked from stacked 120 to 270. So in the simulation, it went from 40 seconds to only 16 seconds. And also the image was retrieved successfully. So that's why we find this compression method and saw that it works. It does do a good compression. And that is basically where we are about NRQR. We managed to fully implement it and automatically. So now everyone can just, if you wanted to test on your computer, you can just change the image path and change the size you wanted. And I also have some example images there. If the Lena image as well, that's widely used and everything. We started to implement the fast corner detection algorithm, but we actually have some questions about it, some implementation questions about it. And I don't know if it's best for us to ask those questions now or wait everyone show their progress to ask them.
We can wait the other presentation. After that, we can continue
Okay.
with the problem. But compression and converting the images gray, black and white, white and black, it so makes sense. Thank you for your work.
Yes, yeah, we shared it because maybe another group could use that idea as well, because for us at least it was helpful, maybe to them they could. So that's basically it. That's how our progress this week. I'll stop sharing now. But any questions, anything?
No, thank you. But
Thank you.
yes, I know the big size our images, our database, and yes, makes sense compressing. Thank you.
Thank you.
And second group is Asude, and are you ready?
Yes. I couldn't prepare a presentation. Sorry about that.
Okay, no problem. You can continue. You can only talk about what you did. It doesn't matter.
Yes, thanks. This week I examined the article on my own and researched other articles. The article we were asked to review is very complex and uses advanced version of the NKR algorithm. Therefore, this week I tried to delve into the article deeply. And I also looked at articles on topics like quantum error, mentioned as subheadings. Also, unfortunate.
Corner detection, I think.
Yes. Also, I wasn't able to have a productive conversation with my teammate, and that's all.
Okay, thank you. Yes, that's the problem. I will talk about later on Discord about this problem. Maybe someone outside can be outside our project group. Yes, we can talk about later on Discord. And thank you for your work. And we can continue with the third group. Simge and Mohammed.
Hi.
Hi.
Hello everyone. I hope you had a great week. We tried to read and understand the paper. When I read the fast corner detection paper, I found that in theory it is simple to understand, but this method has many complicated steps. For example, in the data preprocessing steps, an improved version of the NQR method is used. In this paper, the NQR method is optimized by bit resetting, and the number of qubits is tried to be minimized. I also saw that each steps includes in detail, and these steps are explained in the cited articles. I think we can use them. In general, I think that the method we will use is understandable but requires careful study.
Can you
Thanks.
show me the article? If you upper page. For giving the suggestion other groups, can you show the your paper? Which paper are you using?
Fast corner detection algorithm.
No,
You share it.
no, other method.
I share it in Discord.
Okay, thank you. Okay, thank you for your work, and we can pass it. Last group, fourth group is Emre and Rijan. Is okay?
Yeah.
Yes.
So this week I heavily spent my time. I heavily spent my time learning about NQR and FRQI, the difference between them, and how the algorithm works, the fast corner detection algorithm, like in depth. And my goal for the next, so I also checked the notebooks available, so I'd like to learn how the NQR technique works. And my goal for the next week is to use at least one image from the dataset we are going to use and apply on it the fast corner detection algorithm with FRQI, not with NQR, but with FRQI, and see what happens.
Okay.
Hello.
Hello.
Yeah, I've been a bit unwell till week, so I've resumed my work from today, and I didn't get time to go through all these teammates and group discussion till due to my severe illness. But I did my work on any QR algorithm as I wasn't aware of my group formation and other stuff. So I present that today.
Okay. Thank you for your work.
I will be presenting you the code.
Sorry, I don't understand what you said.
Yeah. As I was unaware of the group and the task I was assigned to, so I randomly did my work on any QR algorithm.
Okay.
And I have used different approaches on that. So shall I present it or from onward next week I should do the task that I'm assigned to.
Okay. Thank you for your work. And Yes, I thanks everybody for the efforts. I want to ask first group, did you see the results are using our data sets? Did you, as I understand, did you you compressed the original image, and did you see did you measure the results? What we'll see?
Yes. We were able to
For
retrieve.
example, triangle, we can see triangle or rectangle. We can easily maybe between triangle and rectangle other images. We can see the easily differences between this type of image.
Yes, we resized it to a 32 by 32 bit. And we used the triangle example, and it was still able to perfectly recognize the triangle. It didn't lose enough information to not be coherent anymore. And with 32 by 32, came back to being feasible to do. I think I uploaded a comment with it, the example, but I'm not sure. I'm trying to look for it now. But we were able to resize it to 32 by 32 and still retrieve enough information to understand that it was in fact a triangle. But we only tested with that triangle, but I think the majority of it will continue be that way. It didn't lose the much information with 32 by 32.
Okay, thank you for your information.
Thank you.
Maybe every group can use the compression the image because yes, we know everybody knows image size is so big. And in meanwhile, I will search new data, maybe small size, small size. And also, I think everybody have problem implementing corner detection algorithm. And I will also try to implement starting this week implementing these images by using this corner detection paper to help everybody. And yes, we can continue to work, but some groups suggest me that without implementing corner detection, they want to continue directly classification part. Yes, it can be, if the result is good, yes, there is no problem for me. And is there any suggestion for the project? Can say, everybody can say, and explain now. Is there any question or suggestion I can? Yes.
Yeah, if you want to, I can share my screen because I found the example image after shrinking the code here. I had a commit with it. If you want, I can share on screen to show how the image became.
Okay.
This code is in a commit on the repository, so everyone can see. This also like example of how big, even after the shrinking, the circuit became really big. But this is the image, the reduced image. So as you can see, you can still clearly see that it is a triangle. It didn't lose that many information.
Yes, it can be.
So, yeah, and this is again the original and the generated by NQR version.
Okay, thank you.
Thank you.
Yes, good work. Thank you, everybody. I will start. I will stop the meeting now. Next week we can continue work. And as I said, I will try to implement corner detection algorithm sources. Yes, to help everybody. I want to effort everybody in the group work together. And sometimes somebody said me my group mates doesn't make anything. it doesn't make sense for me. And if the problem continue for the group mates, I will inform the mentors or leaders, QInterns, for us for stop this project outside the giving this project. And yes, thank you. Good work. See you next week. And yes, see you next week.
Thank you very much. See you next week.
Next week.
Have a
Thank
nice
you.
weekend. See you.
I will share the recording on YouTube channel, and I will share the link on the Discord. Thank you.
Okay, thank you. Bye.
All right, thank you.